Hi, I'm Benny Pinkas from Bar-Ilan University. I'm going to describe work on non-interactive secure multi-party computation, which was joint work with Shia Levy, Ayman Jarus, Yehuda Lindell, and Ben Riva. So for those of you who are not familiar with secure multi-party computation, I'll start with the canonical example that started this line of research, which is the millionaires problem. So suppose there are two millionaires, Alice and Bob. Each one of them has a certain amount of money, and they want to find out which one has more money than the other party. So Alice has X dollars, Bob has Y dollars, and they want to see whether his X is greater than Y or otherwise. So the thing here is that they want to compute this function without revealing any other information. So the only output that they should learn from this function is a single bit, which is 1 if Alice has more money than Bob, and 0 otherwise. And it's interesting to note here that standard crypto tools do not help here. They can encrypt the communication, they can authenticate it, but this just helps them secure the computation from external parties. What they want to do here is prevent Alice from learning anything about Bob's input and vice versa. And just using standard crypto tools is not going to help them in this task. Another thing to notice here is that this problem seems like a toy problem, but in many applications we indeed have to find out whether one input is greater than the other one. If you run an auction, you want to find which bid is higher than the other bids, so you want to compare numbers, okay? So comparing numbers is actually one of the basic tasks that repeats over and over again in many applications. So what do you want to achieve here? You want to run a computation between Alice and Bob, at the end of which they learn some function f of x and y. So Alice has an input x, Bob has an input y. At the end, they learn some function f of x and y, which they agree upon, and they want to learn nothing else. So we need to define what security means here. And actually, tomorrow you're going to hear a talk by Yehuda Lindell, who's going to talk a lot about secure computation. He's going to give you the much more exact definitions and motivation, applications, and so on. Today, I'm just going to glimpse over the introduction to the topic, so just give you a hint of what the definition says. So the definition goes along these lines. It says, okay, what's the best we can hope for? If we had some trusted party that we both believe in, and we know that it's not going to cheat on us, okay, this Santa here, then Alice and Bob could whisper their inputs to the trusted party, who'd publish the output. So he will say, no, Alice has more money than Bob and nothing else. So this is the best we can hope to achieve, okay? What we want to do is to do a computation between Alice and Bob alone that doesn't reveal more than what is revealed in the ideal scenario when we have this trusted party, okay? So in actuality, they don't have any Santa that's going to help them, okay? They say in an ideal world, we would have this trusted party who could help us do the computation. We want to do a computation just between the two of us and leak no more than in this ideal world, okay? So this is what the definitions try to capture. We can also define secure multi-party computation with more than two parties. And here, they each have an input. They want to compute some function of the input. Say it's an auction. They want to compute who wins the auction. And definition is similar. In an ideal world, they'll have a trusted party who will compute the result of the function for them. And the result will be published. They want to do computation between them alone and reveal nothing more than this ideal world. So there are some things to notice here. First, the output of the function is revealed, and it might leak some information, but we assume this is something that the parties are willing to give, okay? So Alice learns that Bob has less money than her, and Bob learns that Alice has more money than him, but this is something they're willing to give, okay? In some cases, this function f gives a lot of information. In some cases, it doesn't give too much, okay? Before just going to do this computation, they have to think whether they're willing to leak the value of f. So basically, all that we're doing in this field of computation, of investigating secure multiple computation, is say, this function we want to compute. We know that if we had a trusted party, we would have been happy to compute it and leak the output of the function, nothing more. Unfortunately, we don't have any trusted party. We want to do computation just between the parties who have the inputs. and we will know more than in the model where we have a trusted party. Okay? So all that we're going to do here is get rid of this trusted party. So surprisingly, we have very strong feasibility results here. So since 82, 86, Yao have shown how to solve this for the two-party case. And then there are other solutions by Goldwasser, Mikhail, and Vigdeson, and Benno, Goldwasser, and Vigdeson that showed how to do it in the multi-party case. And many, many papers on this issue. And I won't give you the details. Yuda Linder is going to talk much more about them tomorrow. One basic common technique is the following. It says, we want to compute a function. Let's first represent the function as a Boolean circuit. Okay? So if we go back to what we learned at undergraduate studies, computability, we know that every Turing machine can be represented as a Boolean circuit. If the Turing machine runs in a polynomial time, the circuit will be of polynomial size. And okay, we take the computation, represent as a circuit. And then we show a transformation that takes the circuit and does a secure computation on it. So by circuit, I mean a circuit just using NAND gates or AND and NOT gates, and that's it. So this seems absurd, but for many functions, we have very efficient circuits implementing them. Consider, for instance, the comparison function, okay? When we compare two numbers, basically we have to compare each pair of bits and do some computation on the results of the comparisons of the bits. So the size of the circuit is linear in the length of the numbers. So we can, comparing numbers between 0 and a billion takes something like 30 times something gates. So it's very efficient. And I can tell you that the most efficient systems for implementing secure computation can implement circuits of size billions of gates in a reasonable amount of time. Also for doing, say, computing the AES function, the AES encryption, the size of the circuit implementing AES is a few tens of thousands of gates, okay? So we can compute secure computation of AES where Alice has the key, Bob has an input, and Bob learns the encryption of his input uses Alice's key and nothing more than encryption, and Alice learns nothing about Bob's input. And this can be done pretty efficiently. And actually, the tools that implement these solutions, they're mostly, some are very early, like Fairplay, others are more recent, but you can specify your computation as a program which is, say, similar to C, and it will be translated to a circuit, and a protocol based along these lines will be applied to the circuit, and Alice and Bob could run the protocol between themselves. Okay, so we're talking about crypto here, so there are parties who want to do bad things, the adversaries, and we consider here two types of adversaries. The adversary which we call a semi-honest adversary is one which follows the protocol but tries to learn more information from the message it received in the protocol. A more powerful adversary is what we call a malicious adversary that can try to do anything that it wants. So suppose the protocol tells the party, say, to choose a random number x and send x to the power of 2 to the other party. Then the semi-honest adversary will indeed choose a random x and send x to the 2. And the malicious adversary can do anything that it wants. Okay? So obviously, it would be easier to prove security against semi-honest adversaries, just trying to prove that they learn nothing from what they see in the protocol. And think about the Alice and Bob, the millionaires problem. Even if we know that the parties are going to follow the protocol, it's unclear how to let them compute who has a bigger input without revealing anything else. Even if you're not going to do what we're going to tell them. How can they exchange information without revealing their inputs and learn who has more money? But of course, it's better to prove security against malicious adversaries, right? Because this is a more powerful model that adversary can take. And in this talk, I'm going to talk about malicious adversaries. Now, there is one other major problem that was overlooked in many initial protocols. And that is that in these protocols, all parties have to exchange many messages between themselves in many rounds of interaction. So the view of the world is like, we have these 5 parties here, and the protocol is composed of rounds, and each round, each party sends messages to any of the other parties. Okay? And this seems nice in theory, but this might be a huge obstacle if we really want to implement this. So suppose I want to run some computation between me and, say, 5 other friends, and one of them just happens to be in the States right now, and the other one is in Japan. So I'm sending my first message to all of them, but the guy in the States is still sleeping, and the guy in Japan is ending his work day. And by the time the guy in the States wakes up, he sends an answer, but the guy in Japan is already went to bed. So but next day, the guy in Japan wakes up, he sends an answer, but the guy in the States is already sleeping. And so the computation is slowed down, okay? Because everyone has to be online to answer messages and send answers. So said it differently, in actual scenario, parties come and go whenever it's convenient for them. And we cannot assume that all of them are going to be online to exchange messages between themselves. Okay? And we want to support secure computation in this model. And in the two-party case, the protocols have many rounds of interaction between the parties, and we want a protocol with just a single round of interaction. One message in this direction, then a single answer. And it's also nice if the first message can be used for many interactions. So the party who sends the first message, say, publishes it on its web page, and any party who sees this web page can, say, send an email back with an answer, and then that first party can compute the result of the computation. And this is what we achieve in our protocols. So this issue of interactivity is actually, I think, to be of major importance. So I think that the difference between interactive versus non-interactive is a qualitative one rather than a quantitative one. So it's much more important to reduce the number of messages from 3 to 2 than it is to reduce them, say, from 10 to 3. Because once you have 2 messages, you can do these things non-interactively without having to wait for the other party. So if we go back to the history of cryptography, Diffie and Hellman came with the notion of public key crypto and key exchange, and they had an interactive protocol for key exchange. But then the major development was the RSA protocol, which enabled you to send non-interactive encrypted messages that the other party could decrypt when it gets them. So in web communication, we can use Diffie-Hellman key exchange to initiate a secure connection. If we're talking about secure email, we must use RSA because the other party might not be online to answer your messages. So if we have non-interactive secure computation, we can do essentially secure computation by email. And okay, another motivation is that if we need an interactive protocol, then the slowest party slows down all of the other parties who in each round have to wait for that party. Whereas if we have a non-interactive protocol, everyone finishes its work, and then we have to wait for the last party to send its result, but the other parties don't have to listen to the communication. If we're talking about load, so suppose I have a server that handles millions of users. If I know that I have to answer them quickly so that they can go on to do their work, I have to set resources for the worst load that I might have to encounter. Whether if I know that I can operate non-interactively, they don't have to wait for my answer, I can set resources for the average case. And some answers will have to wait till I have enough resources, but that's okay because no one is waiting for me. Also, it's good for what we call green computing. So in some times of the day, computation resources are cheaper, okay? So if I don't have to hurry up and answer because other people are waiting for me, okay, then I can wait with my computation until computing resources are cheaper. So it doesn't matter for one of us who just uses one computation, but think about a server who's doing millions of computations. It might save some money to wait with doing them until computation is cheaper. And okay, and the first thing that comes to mind when we're thinking about implementing non-interactive secure computation is to use fully homomorphic encryption. And it's actually unclear how to do this. For the multi-party case, we can indeed encrypt the messages using fully homomorphic encryption. We can do the computation, but for the decryption, we need someone to decrypt it. And if only a single party can decrypt, then he can read all messages. If we need a few parties to decrypt, then they need some interaction between them. So it's unclear how to do that. In the non-interactive case, in the two-party case, there are solutions which use fully homomorphic encryption and PCP proofs, but they're quite elaborate and seem to be impractical. So the results we're going to describe here are a one-pass multi-party protocol. This is work with Shai Halevi and Yuda Lindell, which implements multi-party computation for some general families of functions. We have a system implementing this protocol. Hopefully, I'll show you a demo later. This is a joint work with Ayman Jerus, who's sitting here. And it is secure against malicious adversaries, I'll show that later. And also, there are some issues related to how to implement crypto in the browser, which are quite interesting. And also about efficient protocols in the two-party setting. This is joint work with Ben Riva. And also there we have a prototype which runs as fast as the best interactive prototypes for secure two-party computation. So basically you can get this non-interactivity property for free. You don't have to pay any resources for it. So before I go into our new solutions, I'll go into what people have been doing in the past. So one hack around this is to say the following. Okay, I'm running out of battery here, so I won't be able to show. So we have these parties who want to do the computation. Say that there are farmers who want to participate in an auction. Okay, there are hundreds of farmers here. They're not going to be online at the same time. So we can set 3 servers who are going to be online because we're going to take care of them. And in some initial phase, all the farmers are going to take their inputs and share them among these servers. So this is done non-interactively. This farmer has time. On this day, he shares an input among these servers and then goes to do his work. After all of them has done that, the servers run an interactive computation between them and publish the result. And these are special servers that we can handle, and they are online, so they can do the interaction between themselves. So this has been used actually for auctions between farmers in Denmark and in other applications. And so this is a solution that people have been using. And what we want to do is reduce the requirement to use 3 servers and use just a single server. In the 3 server setting, the solution is secure as long as no 2 of these servers are colluding with each other. And we want to add just 1 server and have a solution which is secure as long as this server is not colluding with many of the parties here. So this is what we did in the work with Shia Levy and Yehuda Lindell. So we have n parties and 1 server. And the communication model is each party comes to the server, does some short interaction, then goes on and doesn't come back to the server until the end of the protocol when it learns the input. So each party comes to the server, doesn't come to the server any time in the future, and then the server can compute the function, output the output of the function. So obviously there's a problem here. If the server sees here the message from the first party, we don't want the server to be able to mimic the part of the other parties and then be able to compute the output of the function. Because then it can say, okay, let's see what happens if the second 2 parties give an output of 0, give an input of 0, input of 0, 1, 1, 0, and so on, and learn a lot about the first input. So this can be easily solved if we assume that there's a public key infrastructure and each party identifies itself using signatures. So that's easy to solve. Now there's a more delicate problem here. Suppose there are n parties, and this is the function we want to compute, and suppose that the first I parties has provided their inputs. So the inputs of the first I parties are these black x1 up to xi here. So these values are given, and the red values are variables. We're still waiting for the last n minus I inputs. So obviously, the n minus I last parties can give any input that they want and compute the output of the function. Okay, this is what the protocol should allow them to do. Okay? Now, assume that there's an adversary controlling the server and the last n minus I parties. He could, try to mimic what they're doing, simulate what they're doing, and say, okay, suppose that this last n minus I parties that I have all give the input 0. Okay? Let's simulate the protocol. The first I parties are not going to participate because they participated in the beginning. They don't have to come again. And then we run the protocol, see what the output is when these last parties give all input of 0. Then he simulates the protocol when they give an input of 0, 0, 0, 0, up to 1, and so on. So basically, he can learn the output of the function for many variations of the input of the last parties. Okay, and this is more than is allowed in the ideal secure model where this, only 1 computation of the protocol is allowed. And this is actually an inherent limitation. We cannot prevent that. So this is something that we put in the model. So in the paper, we defined it quite elaborately, and I won't go into details in this talk. But basically, the definition says the following. If the server is honest, then nothing is learned about the inputs except for the final output of the function. However, if the server is corrupt, and also the last, say, 5 parties are corrupt, then they can learn what we call residual function or residual truth table of the input of the function that is waiting for the input from the last 5 parties. So basically, suppose the 5 last parties are corrupt, they can run the protocol with all 32 options for the inputs if the inputs are binary and see what the result is. So basically, they can learn the truth table for the function, the residual function is waiting for the inputs. This is something that we cannot prevent in this model, but we don't want to reveal anything more than that. So suppose the server controls the last 5 parties, and then there are some parties that he doesn't control, then 100 parties over here. This doesn't matter. The only thing that matters is the last parties that the server controls after the last honest party. Hope this will become clear sooner. So we presented some practical protocols for some general families of functions. I'll show just one example for binary symmetric functions. So this example uses the El-Gamal encryption, where we have a generator G, and the public key of party I is some age I, which is G to the power of alpha I, which is its private key. I hope that people are familiar with this. And with capital H, 1 to n minus 1, we denote by the multiplication of the public keys of all parties. So then to encrypt an input, you just encrypt it with this capital H, which is the multiplication of all public keys. And then what's important to note is, each party can decrypt its key from this general encryption. So each party can remove the contribution of its public key for this encryption. So one by one, they can peel layer over layer of this encryption until they get to the result. And they can also re-randomize the encryption. That's the important thing to notice. And instead of going through this protocol, I'll show you an example. And Tzachi, you should start preparing the demo. Okay. So suppose you want to compute the majority function. So I'm talking here only about binary symmetric functions. Binary meaning that they have binary inputs. And a symmetric function is one where the output doesn't depend on which party has which input. It just depends on the number of parties who have a certain input. So for instance, in binary functions, a symmetric function is one where the output only depends on the Hamming weight of the inputs. So say the OR function is symmetric, the exclusive OR function is symmetric, Other functions are not symmetric, So we're only talking here about symmetric functions. Assume we're talking here about functions with 5 participants. So normally this function would have a truth table of size 32, but since this is a symmetric function, the output only depends on the Hamming weight. So the truth table has a size of 6 for all 6 options of the Hamming weight. And suppose we're computing, say, the majority function. So the first half of the truth table has a 0 output, and the second half has a 1 output. So that's the function we want to compute. The first step of the protocol has the server encrypting each entry of the truth table using the multiplication of all the public keys of the participants. And the server is the last participants. It has PK number 6 here, and randomness for each one of them. So this is just an encryption. Now the first party comes. So suppose the first party has an input of 0. So what it can say to itself is, I have an input of 0, therefore it would be impossible to achieve, to get to this maximal Hamming weight. The Hamming weight is not going to be 5 because there are 5 participants, my input is 0. So I can therefore remove this last entry from the truth table. And to hide from the other parties what I've been doing, first of all, to enable the decryption at the last step, I'm going to remove my encryption from this table. So you see now the encryption starts with PK2. And also to hide from the party what I've been doing, I'll re-randomize everything. This is something you can do with the El-Gamal encryption. Now the second party comes, and this party has an input of 1. And it says to itself, since my input is 1, the Hamming weight cannot be the minimal Hamming weight because I contribute 1 to the Hamming weight. So therefore, I can remove the first entry from the table. And then I'll decrypt my layer of the encryption and I'll re-randomize. So therefore, each party comes, decrypts, removes an entry, decrypts, and re-randomizes. So the table shrinks as we continue. If all parties arrive, then what we get at the end is that the server gets an encryption of the final result of the function encrypted with the server's public key, and the server can decrypt it and learn the result. Now suppose that we have a collusion here between the server and say one party before it. Then we get the encryption of this residual function, what the fourth party generated before the fifth party should remove an entry from this table. Since the colluding, they can together remove these two layers of encryption and learn that the residual function, once we get to the last party, contains two entries of 0 and 1. Okay, but that's the only thing they can learn, and nothing more than that. Okay, and this can all be being rigorously defined and analyzed. Two properties that should be noted is first, I define the parties as parties 1, 2, 3, and so on, but they can come in any order and remove their encryption in any order. Okay, so we don't have to define in any order in which they should arrive. And security follows, since the only thing that the server and the last parties can do is they peel their encryptions from this encryption. And if there is still one party who is honest, we cannot peel its encryption, so there's nothing we can do here. Now, this is nice if we believe the parties to be honest, semi-honest. What happens if they're malicious and not going to follow our protocol? So they can do many things. The server could generate a truth table of a function which is not the one we want to compute, and parties could completely replace the function. Suppose I want the output to be 0, then instead of removing one entry from the truth table, I just replace the truth table with a new truth table that has 0 in all entries. So therefore, the output will always be 0. Okay? This is something I don't want to happen. So to prevent attacks, what we ask parties to do is to add non-interactive zero-knowledge proofs, proving that they've been doing what they should be doing. Okay? So I won't say how you implement non-interactive zero-knowledge proofs. What I can say is that we reduce them to proving that a certain tuple is a Diffie-Hellman tuple. I also want to explain what a Diffie-Hellman tuple is. Okay? And we need the random oracle model here. And how much does this cost? Okay, so let's see. Suppose we want to compute the majority function. What should the first party do? It should prove that it encrypts the truth table of the majority function, the one that we've seen before. So basically, for each of the 6 entries, or the n+1 entries in the general case of the truth table, it should add the proof that it encrypted it as it should. Okay? So basically, we have order of n and proofs. Each one costs a constant number of exponentiations. So the truth takes order of n exponentiations. Then each party needs to prove the O of 2 statement. That either it removed the first entry from the truth table and then decrypted and re-randomized, or it removed the last entry of the truth table and decrypted and re-randomized. Okay? Each one of them costs O of n exponentiations. Overall, the cost is also O of n there. So if we calculate, we get that overall the cost is about, per party is something like 8 times n squared exponentiations. How did we get to this n squared instead of n exponentiations? That's because each party generates a proof which costs its order of n work, but it should also verify all the proofs of the previous parties, and this work can grow to be quadratic, order of n squared. Okay? This is nice, but we wanted to implement things. So actually, in the implementation work, we improved that. There's an easy way to batch many Diffie-Hellman proofs. So to prove that 2 tuples are Diffie-Hellman, you could use short random exponents, combine them together, and then prove that the combined tuple is Diffie-Hellman. And you can also do this for n tuples. I won't go into the details. But what you get here, you get order of n squared short exponentiations and only order of n full exponentiations. Okay? So this is pretty efficient. I'll show you soon how efficient this is. Okay? So suppose we want to use the protocol. So we describe the protocol. It's pretty simple. Okay? You can follow the paper and implement this. And then you can say, use it on the web, on Facebook to say, do some voting among your friends. Okay? However, to do that, you have to read the paper and implement it, and people usually don't do this. So we wanted to do this, to give them a tool to do that. And this is the work I've been doing with Ayman Chavus here, where we actually implemented this. We call this system as call it Canon MPC, for a system for casual non-interactive multi-party computation. Okay? And it can be run as a standalone system or integrated with other systems. So this is the system. Basically, it's a website, canonmpc.org, where you can log in and do a computation. And when we came to implement it, and this is more like a systems aspect of the implementation, we had to think how to implement this system, how to do advanced crypto on the web, in the browser. So there are some ways of doing that. One approach is to implement everything in Java or use JavaScript, or send the parties some application that they should download and run on their machine. In the end, and I'll show you why, we use a different technology called native client from Google, which essentially lets web servers send C code to browsers, and then the browsers run it in a sandbox inside the browser that makes sure that the code doesn't do anything bad with the system, and have almost the same efficiency as C code. So the cost is something like 20% slower than C, according to our measurements, and still it's a pretty secure code. Now the downside right now is that this native client technology is only implemented in Chrome, the Chrome browser. Firefox now has a competing technology which they announced. I'm not sure if it's available, called Odin Monkey. Explorer doesn't have anything, but there's no, I mean, you can implement, our protocol in native client as we did. Some other people could implement it in, or we could implement it in Odin Monkey once this becomes available. And people who using the protocol in different implementations could work together. So we just demonstrate, how you do it with native client, but you could also implement this in Odin Monkey and work together. So why did we use native client? So let's look at different technologies that we have. Suppose you want to implement crypto in a native app that people have to download. So in terms of usability, that's pretty bad because people have to download an application and install it on their machine, and it's not seamless. Security is bad because this application can do everything that it wants on your machine. Performance is great. Okay? Suppose that you're using Java. Usability is mediocre because not everyone has Java installed. Security is not that good. There are lots of exploits known against Java. And performance is also not as good. We've seen it's about 5 times slower than what we're using. Okay? Suppose you want to use JavaScript. JavaScript is great in usability. We all use JavaScript all the time in pages that we see. It's pretty good in security. It's very bad in performance for public key crypto. Especially in terms of memory, we couldn't do anything with JavaScript. Okay? And with native client, you get pretty good usability. Once you have Chrome installed and you enable native client, you don't feel that it's working. Basically, the server is sending you pre-compiled C code that is run on your machine, but you don't notice this. Security is good. There are no known exploits against native client. And the performance is just, say, 20% more than the best that is possible. So this seems like the best of all worlds. So this is how we implemented. So this is the system. So to use the system, we first have to go and register. So basically, you put a username, password, and then you generate a private key. The key is generated by you downloading code, which generates the key on your browser, then encrypts the key with your password. This is what you have, and stores the encrypted key on the server. Of course, you can store it locally, but then you might lose it. So this is just a design decision that we had. Now, how do you run the protocol? So now I'm going to try and run a demo. Here I'm connected. Let's see if it works. So this is the system. I'm registered here as user 1, and I want to invoke a new protocol. Okay? So I'm invoking a new protocol. Let's call it sample protocol. And I'm inviting 2 other users, user 2 and user 3. And I continue. Now I should fill the truth table. So this is going to do an OR between 2 parties. So the truth table is of size 3, okay? Because there are 3 possible values for the Hamming weight. So now I'm going to put here the truth table for the OR function. And now I'm gobbling the table. Here I get the gobbled table with 3 rows. And now I start the protocol. This is just communication. It should hopefully finish soon. Did it finish? Yeah. It did. So basically what was done, and this was done not when you waited, but when I press you on gobble table, this was instantaneous, is encrypt the truth table, okay? And then add 0 knowledge proofs, proving that it did encrypted this truth table of the O function. Now, I log on to a different user, and now Tzachi was sitting there. Yeah? You did it already? So what he did, he logged in as user number 3 and entered an input of 1. And now I'm going to log in as user number 2. I log in. See, the wireless network is pretty slow here. Okay, I'm user number 2. I want to participate in the protocol. I'm inviting to this sample O protocol. I'm getting a truth table of size 2 because he removed 1 entry from the truth table. My input says it's also going to be 1. And now I'm getting the result, which is 1. What I've been doing, what was done here is that first I've checked the 0 knowledge proofs that were generated by the party who initiated protocol and by Tzachi, and then I removed an entry and decrypted it. Okay? It was all instantaneous. Now let's go back to the presentation. So this is what we do here. This is just, in case the demo wasn't working. Okay? So what about performance? So we implemented crypto in the most basic way. We used Shoop's NTL library. We worked in ZP star instead of elliptic curves because that was just simple to do. We didn't do any optimizations, even not the optimizations that Shoop's implemented, because it wasn't easy. Let them go through the knuckle compiler because knuckle tries to protect the code from any, doesn't let you access the machine itself, use any assembler code. So we didn't use any optimization. Okay, and the performance, say for 10 participants, key generation takes 5 milliseconds. The first party who generates a table of size 10 and does the 0 knowledge proofs takes like 1.2 milliseconds. And for each of the other parties, it's something within half a second and a second, okay, to generate the table and proofs and verify all proofs that it received. And I'm sure you can easily, reduce these numbers by a factor of, say 50%, okay? So, and this is, in terms of user experience, this is like, it's pretty good. You cannot do better than that. Okay. So this was about multi-party computation, and now I'll describe a little about two-party computation. This is the work with Ben Riva. And what you want to do is reduce the number of interactions we have in secure-to-party computation to just 2 interactions, 2 messages. And also the first message can be used with many parties. Okay. So what this enables, as I said before, say implement everything by mail. Or say I publish a message on a web page and then people can answer me by mail, which we actually did. Okay. Yuda's going to talk about this more tomorrow. I'll just give you highlights. A major tool that we're using is oblivious transfer. For those who are unfamiliar with it, might sound surprising at first. So oblivious transfer is the following protocol. There's a sender and a receiver. The sender has 2 inputs, say x0 and x1. The receiver has a single input, which is a single bit, either 0 and 1. At the end of the protocol, the receiver learns the input of the sender that corresponds to its input and nothing else. So if the receiver's input was 0, it learns x0, otherwise it learns x1 and nothing else. And the sender doesn't know which input is learned by the receiver. Kilian have shown that secure computation can be based on oblivious transfer alone, and indeed many secure computation protocols use OT extensively. And there is fully secure OT that is secure against malicious adversaries. Now, how does secure two-party computation go? Again, details tomorrow, but the basic idea is the following. one party generates a logical circuit computing the function. Okay? So there's a circuit, say, comparing two numbers. Then it garbles the circuit, meaning that instead of passing 0 and 1 values on the wires, it replaces them with what we call garbled values or random keys. Okay? So instead of passing 0 a specific wire, then say a random number of size, say 128 bits is passed. And then the parties run an oblivious transfer where the second party on this side learn the garbled values that correspond to its input. And then it can, after this oblivious transfer, it can evaluate the circuit. How this is done, you learn tomorrow. Okay, we only care about the general structure here. Okay, so in this, at least in the semi-honest case, it's very easy to get non-interactivity here. So if I go back here, we had 3 messages. This way, that way, and this way. If we reorder the messages, we can get non-interactivity. This message will be the first one on this side, and the other 2 will send answers. And you look a bit at this and see if you can actually do that. So by sending the first message of the oblivious transfer first, and then sending the answers and the circuit, you can achieve non-interactive secure computation here against semi-honest adversaries. Now, what about malicious adversaries? So the basic protocol one of the protocols to achieve security against malicious adversaries for YAO goes along the following lines. So we want to check the circuit. So the party who generates the circuit generates many circuits, many of them. And it commits to each and every one of them. And then the other party asks the first party to open about half of these circuits and verify them. So we ask him, okay, you see these red circuits, please open them and I'll check that you've constructed them correctly. And afterwards, they evaluate the other circuits. So basically what we say here, okay, and then they compute the output as the output, the majority of the values. So the idea here is, okay, I'm checking here half the circuits, okay? If even one of them is cheating, I'm not gonna run the protocol. So to cheat, the first party has to somehow not be caught when half the circuits are checked. On the other hand, on the last step, they're going to evaluate the remaining half and output the majority. So to be able to cheat, at least 1/4 of the circuits have to be corrupt in order to influence the majority when these are being evaluated. Okay? But none of these corrupt circuits should be among those who are checked in the first step. So the party who constructs the circuit has to be very lucky to put many corrupt circuits here and have none of them being checked in the first step where half the circuits are being checked. So this is the basic idea here. And there are many other issues, especially verifying the consistency of the inputs for these many copies of the circuits. The problem here is that the protocol is non-interactive. Just look at the first step. I'm committing to many circuits. Then you ask me to open, say, half the circuits. Then I'm opening these circuits. So here alone, we have 3 rounds, even without counting the oblivious transfer. Okay? So how to do non-interactive secure computation, or NISC, for malicious adversaries? So one option is to add zero-knowledge proofs for each step there. So this is possible, but the zero-knowledge proofs have to be what we called non-black box proofs, meaning that we have to look in the intricate details of each of the cryptographic primitives that we're using, and the cost is going to be polynomial but very high. Okay, so it's not going to be efficient. And there's very impressive work that actually initiated our interest in this work, in this line of work. This work was done by Yuval Ishai, Al Kushilevitz, who are sitting here, Ostrovsky, Prabhakar, and Sahai, and they showed how to do non-interactive computation in a black box way, without using these inefficient zero-knowledge proofs. So they used pretty powerful techniques, such as MPC in the head and randomized encodings, and they achieved what seems to be excellent or optimal asymptotic efficiency compared to the semi-honest protocol, which is the best you can hope for. You just increase the overhead by a polylogarithmic factor. So asymptotically, this has excellent performance. Okay. And it's all based on generic assumptions, not on specific assumptions like the Diffie-Hellman assumption. The exact cost of implementing this is unclear because it's unclear to us, and I guess to maybe to everyone, how much it's going to cost us to implement all of this with all the constants. Okay. So when we thought about implementing NISC, this seemed like a too hard way to go through. So instead, we built another construction that also results building a non-interactive secure computation from fully homomorphic encryption and PCP, but both of these are not very efficient in practice. So we don't want to, we also don't want to implement them. So what we do, we did a NISC protocol, secure against malicious adversaries, and it's based on cut and choose and a specific assumption, not a generic assumption, the decision Diffie-Hellman assumption. And the overhead is linear in the security parameter, not polylogarithmic, but rather linear, which is higher asymptotically. Yet everything is rather simple, and the implementation wasn't complicated, and we could actually check how efficient it runs. And when we compared the implementation or the performance to that of the best known interactive implementations of secure computation, we got about the same overhead. So say for implementing a secure computation of AES, okay, which is quite complex, secure against malicious adversaries, where this is where the major cost comes, the best known construction that, implementation that runs in a constant number of rounds takes something like 192 seconds, and our implementation takes 165 seconds. This is not an exact comparison because they run on different platforms, okay? But it's safe to say that they both have the same order of magnitude the performance is in the same order of magnitude. So basically, we get here non-interactive secure computation for free. We don't pay more than you pay for the best interactive secure computation. Okay. Something else that we did is revisiting definitions and finding some new attacks, but we're not going to talk about this here. So I just described to you the highlights of the protocol. So basically, we want to do this cut and choose without interaction, choosing some of the circuits and checking them without doing this interaction. So we do the following. The party that constructs the circuits constructs them in the following way. For each circuit, it either chooses a random seed, say seed I for circuit I, that defines all the randomness that it used in the generation of this circuit. All garbled values, all keys, everything that's done in the oblivious transfer. It also chooses a key I, which encrypts the oblivious transfer answers for this circuit. Now, if you have this first value, seed I, you can compute the circuit and verify that it's indeed runs what you should be doing. However, you cannot evaluate the circuit unless you have this key I. Without the key I, you don't know the answers to the oblivious transfer, you cannot evaluate the circuit. On the other hand, if you learn key I, you can evaluate the circuit, but you cannot check it without knowing seed I. Okay? So what we do, instead of doing oblivious transfers for each of the inputs, we also do an oblivious transfer for each circuit, where the party who runs the protocol can either learn seed I and then check this specific circuit, or learn key I, where it can evaluate the circuit. And we can do this in parallel to the other oblivious transfer. So basically, for each circuit, we have this seed and this key. In the oblivious transfer, you learn one of them, so you can either check the circuit if you learn the C, or run the circuit if you learn the key. And you can do this together with the other oblivious transfers. And there are many other issues, like verifying that the inputs are consistent among all circuits. But I'm not going to describe how to do that. So we implemented everything. So what can we see here? These are circuits for computing the edit distance and at the end for AES. So the runtime of generating the first message for the oblivious transfer is linear with the size of the input of the first party. The runtime of generating the circuit and for evaluating it is sort of linear in the number of non-exclusive OR gates in the circuit, because there are ways to evaluate exclusive OR gates almost for free. So basically, the size of the circuits affect this side of the table, and the size of the input affects this side. And as I said before, for computing AES, it took about 165 seconds, which is better than the best interactive constant system that we have. But we measured other things than they did, so we can say it's about the same time. And the implementation was it didn't take Ben a lot of time to implement this. It's pretty straightforward. Okay, I see that I'm in battery stretch, so it's time to finish the talk. So I'll summarize. I think that the interaction in secure computation is a major problem. Okay, and one-pass or non-interactive protocols are much preferable, and also, in addition to being preferable in practice, they're also interesting in theory to examine how efficient we can make them. There are some inherent limitations on this model. As I showed in the multi-party case, the server and the last parties that collude with it can learn the residual truth table of the function. In the multi-party case, we show the practical protocol and actually an implementation it's just I showed it for symmetric binary functions. There are other constructions for other families of functions, but we don't know how to implement all functions in that way. And for the two-party case, we can implement a generic protocol for all functions using specific assumptions like the DDH, and basically get the non-interactivity for free. The performance for malicious adversaries is as good as the performance for a protocol that has interaction. And that's the end of the talk.